Hey, good. How you doing, guys? My name's Alejandro Velasco. I'm in Group 3, along with Mariela, Daniel, and Michael McCoy, and we're going to be talking about our project, the safety helmet. So the motivation for our project comes from data that we found on the NHTSA website that shows that in 2017, per registered vehicle, the fatality rate for motorcyclists was 6 times the fatality rate for a passenger car occupant. Over 5,000 motorcyclists were killed in a motor vehicle traffic crashes that same year. They also estimate that currently helmets are only 37% effective in preventing fatal injuries. Smart helmets currently on the market really don't focus on safety and are very expensive. So here's a couple of similar projects that we modeled our own helmet after. We got the Kraus Helmut X1, the Quinn Design Spitfire, the Jarvis XAR, the Scully Phoenix AR. And we took one or two things from each of these helmets and added them to our helmet. Our goals and objectives is to research, design, and build a state-of-the-art safety helmet in a timely and efficient manner. We're going to use a minimum amount of sensors to detect when objects come into close proximity and alert the driver via OLED display, sound, or an LED light whenever it occurs. We're going to have a crash notification system using sensors and helmets which will communicate with mobile application via Bluetooth. A thermal camera along with eye detection technology is going to be able to detect when a person is falling asleep at the wheel. And finally, have our design be user-friendly and be able to be used worldwide. The specs that we're going to have for our project will be simple enough for the average person to operate. The setup time for everything should be no less than 30 seconds. We want our smart helmet or our safety helmet to communicate with the mobile device app via Bluetooth 4.0 and have it equipped with a 128 by 64 pixel OLED LCD display. 2 ultrasonic sensors, one located on each side of the helmet to cover any dead spots of up to 3 meters. A 3-axis gyroscope sensor to detect if the rider has been involved in any kind of accident. When the accident occurs, the MCU will notify the mobile app and contact the phone's emergency contact. Eye detection monitoring using an IR camera that's going to be powered by a Raspberry Pi. And some of the challenges that we had, some of the challenges that everybody had, is going to be the COVID-19 pandemic. We pretty much, once we started Cedar Design 1, a couple of weeks after, everything started getting pretty crazy. We have a limited budget, and we didn't have any equipment to perform testing on our hardware until recently. We just recently got the hardware a few days ago. The shipping turnaround times also were pretty big. We actually ordered some components from China that we never received, so we had to scramble and get some stuff local. It's a little bit more expensive, being we're in a limited budget, but that's what we had to do. Virtual meetings were allowed in the beginning. Only virtual meetings were allowed in the beginning, and until recently we started meeting face to face while still adhering to social distancing requirements. And I think the biggest challenge that we're going to have is going to be having our PCB fulfillment and testing it in such a short period of time. We're not going to be able to really get a second one sent out to get done, so we're hoping that we get it successful PCB that first time around. For the hardware selection, proximity detection, we narrowed it down to 3 different ones, but we ended up going with the HC SR04, being that it was very affordable and we already had experience with it in junior design. For the motion detection, we ended up going with the MPU 6050 3-axis gyro. It also was very affordable, and it was one of the more reliable and accurate sensors that we researched.
In our design, we want to have indicators in order to make the motorcyclist aware of their surroundings and to convey information. The OLED display will show a warning or danger alert if there is, for example, a vehicle in the blind spot. It is also going to be used to display temperature. If time permits, navigation information will also be displayed. We decided to go with the OLED display that is shown in this slide because of its better picture quality and resolution compared to an LCD display. It also has a small form factor, so it won't be taking up a lot of space. Two LED lights are also going to be incorporated into our design, and they will serve as warning indicators. Like, for example, if the ultrasonic sensor detects a car in the blind spot, they will go off in order to make the motorcyclist aware. They will also be used for debugging purposes in the PCB design. For our speaker design, we decided to go with having regular 3.5mm earbuds. Earbuds are easy to find anywhere. They are also economical and they have a small form factor. Since the microcontroller that we're using doesn't have a built-in DAC, a DAC will be needed because audio is an analog signal. We decided to go with the MCP4725 12-bit DAC module. This module uses the I2C interface. The DAC will change the digital data from the microcontroller into analog sound data. This DAC will be connected to one of the pins of the microcontrollers. We also included a sound amplifier into our design that will be connected to the DAC. We decided to go with the LM386 audio amplifier. This amplifier will be used in order to increase the sound volume so it's loud and clear. This module requires a supply voltage of 5 volts and it has an amplification gain of 20. For the wireless communication between the application and the MCU, we decided to go with the HC05 Bluetooth module. This is a well-known module. It uses Bluetooth 4.0. It uses the serial communication, so it makes it easier to communicate with the MCU. The frequency in the transfer data is fast and meets our requirements. Also, the range is sufficient for our design.
For our power supply, we decided that we were going to be using the motorcycle's 12-volt battery as the power source. And we're going to have two adjustable voltage regulators, one set at 5 volts and the other at 3.3 volts, that are going to be controlling the power to our PCB and components. And we went with the 12-volt battery. The motorcycles, just for convenience, easier to use. The rider doesn't have to remember to charge the safety helmet whenever they're not using it.
This is our overall block diagram of our design. As it was shown in the previous slide, a 12-volt battery will be used for the power supply. Two voltage regulators will be needed because different components and modules require either 3.3 volts or 5 volts. Different peripherals will be connected to the microcontroller as shown, and this includes the different sensors, the speaker, the display, the Bluetooth module, and the Raspberry Pi. The camera won't be directly connected to the microcontroller, but instead it will be connected to the Raspberry Pi. And if the camera detects that the motorcyclist is falling asleep, it would send a signal to the Raspberry Pi, and the Pi will send a signal over to the MCU.
The microcontroller is one of the most important pieces in our project, so we decided to look into more well-known microcontrollers in the market. We looked into the STM microcontroller, the ATS from Microchip, of course the MSB430 from Embedded Systems. We consider power consumption since even though we're planning on eventually having the system powered straight from the battery of the motorcycle, It's always important to save power. As we can see, STM is a very powerful microcontroller, has a 48 megahertz clock, but the power consumption is very high. ATS has a little less power consumption, but still very high compared to MSP430. Same clock speed. Although they are cheaper, we decided to go with the MSP430 because we have experience from embedded systems class, and also the power consumption is very low compared to the others. The microcontroller software, first we decided to program it using register level programming, and that's why we didn't use other frameworks such as Energia or Arduino, because we want to get more experience in register level programming. The way it's going to be programmed is using a software interrupt. So when an emergency situation or some sensor detecting nearby vehicle or sleep detection through the Raspberry Pi through the computer vision process will set an interrupt, then the interrupt service routine will respond accordingly. Another feature will be controlled by the software is the OLED display that will be placed inside the helmet, and that will display some important information such as a car in the dead spot, and we might add also navigation if we have time. You can also display the temperature on it, since one of the sensor already has a temperature. It's just an additional feature. The microcontroller will also communicate with the mobile device via the Bluetooth, and it will send, in the case of emergency, it will send a signal to the mobile app to send emergency message to a preset emergency contact from the settings. And it will also play sound, so when a rider is detected that is falling asleep, sleep detection, it will play sound to wake them up. For the microcontroller peripherals, we decided to add a 32 kHz crystal oscillator for more accurate timing procedures. We also decided to add two LEDs for debugging and errors. For programming the microcontroller, we are going to use the JTAG programmer provided in the development kit. We did not design the JTAG programmer to save time and money. We also have a power switch that will cut off the battery to power it off, and some push buttons to control the settings and the interface of the system.
One important feature that separates the safety helmet from previous safety helmet implementations includes the incorporation of computer vision. This module will trigger the microcontroller to perform a waking routine if the user is detected to be falling asleep. The major workhorse of this module is the Raspberry Pi. This system gives us all the tools we need to integrate computer vision features, as well as performance to process several frames of the user's eye region. Next, we will take a look at the No IR camera. The choice to use an infrared light camera came about when our team was discussing how the suboptimal lighting conditions within the helmet could greatly impact the performance of the eye detector. The use of the No IR camera will allow us to capture high-resolution images without being too concerned about the lighting conditions of the camera. This camera includes an 8-megapixel sensor as well as a small footprint, which will be a plus when we start integration into the helmet. This next slide just shows a brief illustration of how the two components of the module will be interfaced. For the software, we will be using an open source library called dlib, which houses many machine learning and image processing capabilities. We will be using the dlib facial landmark detector, which will first localize the user's face and then extract specific facial features. Once the features are captured, we will index the features that include the eyelids of the user. From here, we will perform an aspect ratio calculation, which will output a scalar value giving us information on whether the user is falling asleep.
Here's our schematic of the microcontroller and the connections of the different pins that we will be using. The schematic was designed using KiCad, and this specific schematic footprint was obtained from the TI website. This next slide shows the schematic diagram of the different components and peripherals, as well as the different pins and the different tags of where they're going to be connected to in the MCU. Outlined in red are the different peripherals, such as the different sensors that we'll be using. Block diagrams for the voltage regulators are outlined in green, and in blue is a block diagram of the ZFET pins that will be used to program the MCU. This is our PCB design. It was also designed in KiCad. It has a small form factor. It measures 61 by 66 millimeters. It is a 4-layer PCB. There will be numerous pin connectors in the PCB that will be used to connect our different sensors and modules to the microcontroller. Because the lab in campus is closed and we didn't have access to the different lab equipment such as the oscilloscope, we still don't have the physical PCB. We didn't want to spend money and order it until we were able to get the testing equipment. We wanted to make sure that we were able to test all the components before we placed an order on the PCB. The testing equipment actually came in earlier this week, so we're going to order the PCB in the next couple days. It will be ordered from YLC PCB. They provide fast shipping, and we should be able to get it within a week. And since we currently don't have the physical PCB, this slide shows the 3D design of it and what it should look like. As you can see, we decided to go with, for the resistors and the capacitors, through-hole components, since it will be easier to solder and also they're easier to find.
For the mobile application, we decided to use Android. We decided to program for Android on Android Studio since we have some experience using it. The main purpose of the mobile application is to respond in case of emergency or by sending an emergency message to a preset contact that we'll set in the settings. We might add some extra features such as navigation and playing music if we have time. For the user interface, we decided to go with dark colors since it's saving on battery life and it's also more comfortable for the eye. As you can see, we have the main screen which will display the important information about the helmet system. Then we have the configuration screen when the user can set up, configure the app and also set the emergency contact. The navigation button is still in consideration, and if we have time we'll implement navigation inside the app.
This slide lists out the steps that the user will take, as well as the steps the application will go through to connect to the safety helmet system. First, the user will navigate to the configuration page of the application and enable a Bluetooth connection. The application will check if the device has already Bluetooth enabled. If it doesn't, it will enable Bluetooth. Once a Bluetooth is enabled, the application will begin the discovery for any nearby Bluetooth devices. The application will go through each device and compare it to the known MAC address of the smart helmet Bluetooth module. If there is a match, the mobile application will pair to the smart helmet. Once the pairing is completed, the connection information is stored for future automatic pairing. Next is a brief rundown of the goals and milestones from the end of the previous semester to now. Much of the component testing and design was completed last semester, so much of the work left is mainly system integration and final testing. We are on track to completing the project before the final presentation date. Next is an outline of the expenses for the project. These are just the current line items that we have so far, but we seem to be on budget. We still need to record the cost for the PCB, which will be ordered soon once we do a final review of the design and layout.